Good evening, everybody. It is Obi-Wan Pez for N Simplex Pachinko. That was not on. Okay. How's everybody doing? We are having a pretty good night, although my AOMA partition assistant is not cooperating, so yay. Trying to create a new partition to get a boot disk worked out, and yeah, it doesn't want to behave. Not a big deal, but like I said, hope everybody's week has been going all right. We got fun stuff going on at school. Just about to finish up our final week of. Just about to finish our final week of school here. And all of the parts for my new rig have finally arrived. The only problem is that the case is still out. So, new rig is not particularly for, you know, streaming this. This is not so much of a problem. But it really does struggle quite hard on game nights. I'm sure you all have noticed. So we're looking to make it a much more smooth and interesting experience when we start doing more, or when I'm doing game night stuff. And over the winter and over the summer, there's a good chance that I can stream at least a couple more times a week. We'll see how it goes. I may, on the other hand, decide to actually get a new project off the ground and get my ass into gear. So work toward doing that. Alrighty. Well, if anybody has anything they want to work on tonight, let me know. In the meantime, we're going to be looking at working on one of these other things. Let's see. Let's go to elementary geometry. Because starting in this is the best surefire way of getting somebody in here to say, hey, how about working on this instead? And please do, for that matter. Alright, we were working on Theorem 7. Come on now. There we go. Alright, Theorem 7 states negative a times b is going to be equal to negative parentheses a times b for all a and b in real numbers. Alright, and the way to start on that one, we said, here we're saying that negative parentheses a times b is the additive inverse of a times b. So that's going to be equal to 0 when you add those things together. And likewise, a times b plus negative parentheses a times b is also going to get us 0. Alright, we are allowed to use the things above. So what else have we talked about up here? Cancellation law of multiplication. Zero product property. Cancellation law of addition. 0 has no reciprocal. Additive identity, multiplicative identity. Commutativity distribution. Mm-hmm. So with this, say that 0 is equal to a times parentheses. No, other way. A plus negative A. No, I can't do that, can I? Not yet. Because we haven't isolated the negative to just A by itself. Can do it here, though. So if we say that negative A times B, and then left add A times B equals negative parentheses A times B with left addition. Of A times B. Okay. Alright, I got that. I see a foothold. So here on the left, we now have B, which can be factored out on the right. So reverse of distribution. We have a negative A here, plus A here. And this leads us to the fact that A plus negative A is equal to 0 times B is equal to A times B plus negative parentheses A times B, which is equal to 0, because that is our cancellation law for addition. Okay, so left addition to both sides. Use the idea for additive inverses. Wait, hang on. That belongs in the next line. Oops. Just leaving pieces behind, it's fine. Oh, come on. Come on. Here, the left-hand side, we use distribution. Specifically, we factored out a greatest common factor. Alright, then we use additive inverses on the right to say that AB as a whole plus negative AB is going to be equal to 0. And then on the left, A plus negative A is going to also be 0 times B. So then 0 times B is equal to 0 equals 0. Alright, so therefore we're going to show, or we have shown here, that negative A times B is going to be the same as negative parentheses A times B. We're ending up with In both cases, 0 on either side. So let's see, just one more case here. Right, a times 0 equals 0 for all a in the real numbers. So that's what we got. All right, 0 times b. Same deal. Technically, it's on the other side, but oh, there we go. Yep, 0 times x equals 0. Now we already had that, I guess. All right, anyway. Okay. Okay. So we're gonna get. Okay. All right. So theorem 8. We have parentheses negative a times parentheses negative b is equal to ab for every a and b in the real numbers. Just give me a second here. I got something going on out there. Hey, sorry about that. Kiddo's a bit tired. And they wanted to stay in the same room for the night, and it's a school night, and she's tired, and he's tired, and it doesn't go well. Alright, well. So in terms of the theorem 8, we've got negative a times negative b is equal to a times b, as long as a and b are real numbers. So based on what we said in previous stuff, I would argue that we kind of want to go the same route we did on the last one. And yeah. So I think we want to go the same route here and say that we're going to start with our negative a times negative b is equal to a times b, and then again do sums of equals. No, that's not an O, it's an E. Okay, and then here, what we want to do on both sides again is add something. In this case, we want the negative of a times b. Yeah, it was a smooth move. And add it to both parts. I think we use Theorem 7 to say that negative parentheses a times b is going to be equal to negative a times b. So negative a times b is equal to negative a times b plus negative a times negative b is equal to, here again we have additive inverses, so this is going to be 0. And that's on the right. Technically you should only change like one thing at a time, but you know, most people don't care. So for the left side we want to do Theorem 7. And for the right side we want the additive inverse, which gets us 0 from things that have the opposite sign as each other. And then over here we have negative a, which we can factor out from both sides. Not from both sides. Factor out from both terms. And that leaves us with a b plus a negative b, which equals 0. And then b plus negative b is going to be 0 by additive inverse. This was distribution, factoring, and this was 0 times parentheses negative a, and negative a times 0 is going to be 0, and whatever definition of 0 we call that, right? Theorem 1. So here we can call it the same thing. Sorry, I realized I had a message that was supposed to go to a student several hours ago. That was off-putting. Pardon me. Well, man, it's kind of a dead night, isn't it? Had to resort to stripping. All right, so we got Theorem 8. All right, Theorem 9. Alright, so Theorem 9 states the reciprocal of the product is the product of reciprocals. So here we have AB. A times B, all raised to the negative first power, is going to be equal to A to the negative first power times B to the negative first power. So with this, I think we're going to, again, do the same basic idea that we did for addition, but this time with multiplication. So here we can do a left multiplication of, we don't have like a, we don't have a power rule for this. Excuse me. But we left multiply a times b times a times b inverse. I shouldn't say inverse. Raise to the negative first. Right, this harkens back to the stuff we did before. We're looking for multiplicative inverse. Multiplicative inverse. Okay, so we're going to left multiply on this side as well, a times b times a inverse times b inverse. Okay, in this particular case we have a thing and its multiplicative inverse, so that's going to get us 1. Alright, this is going to be product of equals. Ahoy, Mr. I Love BBQ Chicken. So this is Elementary Geometry by Edwin Moyse. It is elementary geometry from an advanced standpoint. This was a class that I had to take as a math education major, and basically it works kind of the same way as abstract algebra, where at the beginning we start with very basic definitions of how things work, and then start building from basically nothing all the way up. And I think the point of the class was really to show us how far like this whole breakdown goes. I did not really get that at the time, so. All right, here we can do a commutative property. For multiplication. 26x, sure. What precisely do you want to know about set theory? So if we commute the a to the negative first power and shove it all the way on the left, and then we multiply by our a times b in parentheses, and then multiply by b to the negative first power here. Right, what about functions? On the next step we can do multiplicative associativity. And we could say that here we have a to the negative first times a can be grouped together out of these, and that says that again a to the negative first times group a times b can be rewritten as grouping a to the negative first times a times b. We can also then group b with b to the negative first. right? So b multiplied by all the rest of this stuff times b to the negative first, we can then group the last two together. So this is going to be 1 here, and this is going to be 1 here, and we're multiplying, and so 1 times 1 equals 1. We know this from multiplicative inverse. And then 1 times 1 is equal to 1. 1 equals 1 is a great big check. And that is going to be allowed through multiplicative identity. Okay, so that gets us through Theorem 9. Awesome. Okay, so okay, let's move. We can move this back up and over to slide we prepared for tonight. So so if you're just talking functions, so we have this input set over here, and we got an output set over here. If you want to talk about the set of all possible input values, set of all valid input values is going to be our domain. And the set of all received output values, the ones that you actually get, is going to be a range. So again, you got all these range values that are in the output set look like this. Now granted, if you're not actually going to get those particular values, why would they be in the output set? Well, they wouldn't be technically in the output set, but nonetheless. I believe it's kind of where our concept of hmm. Okay. Yeah, this is where I get kind of weird sometimes. Uh, so for an actual function, right, you've got your set of inputs which match to your set of outputs. F is your mapping, which goes from one side to the other. We've got our domain to our range. The weird thing is that this is really like our output values, or the range is really like the image of f. So it's the things that actually come out of the function itself. There's also another thing called the codomain. which is going to be the, technically we could call this a superset. Of the range. In which the function has been restricted to fall. The way that I usually think about this, and that may not be correct at all, but the way I usually think about it is that this is kind of like a first guess. You know, we call the codomain like all real numbers, but it could be that you've got something like a square root function where you're like, well, technically the square root function is not going to include all real numbers. But the codomain is going to be all real numbers because that's the set over which we're working. So generically, you can say, all right, a generic function in this particular thing is going to go from the real numbers to the real numbers. And then when we determine what kind of function we have, we'll restrict our image or the range to be the actual values that actually come out. I need some stuff for my hand. And Blainland, yes, we will talk about Taylor series in just a second. Come on. Alright, we are once again hashtag not sponsored by Hardcore Hand Care, Greenland, New Hampshire. No. Come back anytime you want. It's okay. Now, this is just the last math class he has to take, officially, I think. And my shoulders drive me nuts. Okay. Okay. Grr. That's not what I wanted. Okay. Okay, so with functions, we got all these rules that apply, right? So our codomain is going to be the superset of the range. The function has been restricted to fall within this particular thing, whatever it might be. So we decide what our codomain is going to be when we say, all right, we're only doing stuff with, let's say, integers or let's say real numbers. So we could just kind of decide whatever it is that we want to do. And then for our particular function, the range is the stuff that actually comes out. So yeah, my example from earlier of saying like the domain of a square root function is going to end up being from 0 to infinity. We're just going to call it all real numbers, well, all positive real numbers. And our codomain can be, again, either we could just say, well, it's real numbers, or we could say it's only positive real numbers. And then a particular function, like a particular square root function, may actually use different values. So for instance, if f of x is equal to, 3 square root 2 times x minus 1 minus 8, something like this, we would want to say, for instance, that our domain is going to be that x could be, in this case we have to look at it and say, well, x plus, minus x minus 1 has to be greater than or equal to 0. So we know that x has to start from 1 and then go off to infinity. Our codomain is going to then be, well, again, without doing an analysis of what's going to happen here, we could just say it's going to be all real numbers, right? Our y values are going to correspond with some set of real numbers. Don't really much care. Then, to get the range, we can say, okay, now we have to do an analysis to figure out what we're actually going to get out of this function. So if we plug in from 1 off to infinity, what's going to happen? We're going to get all positive, non-negative, all non-negative real numbers come out from our square root function. So from 0 up to infinity, and then the multiplied by 3, it just changes the rate at which it moves. So that doesn't really change anything in terms of the range. But then we shift down 8. So we're going to start from a received value of -8 and then go off toward infinity. So the codomain is just basically like, what are the acceptable values that we're going to have? What's acceptable to you? Are we working with real numbers? Are we working with complex numbers? Are we working with just positive integers? Like, what is it that we're trying to use? So sometimes you may even call a codomain and say, like, what we really care about is, for instance, we're dealing with money, and we're dealing with sales figures. So what we want are positive numbers that only have up to 2 decimal places. So that's going to be like a really weird restriction. Yep, I got it. So that's going to be our domain and range for this particular function. and the codomain. So like we choose this. This is what comes out of the function. So actually do the function analysis and say, what are we actually going to get out from this function? And then that's your range. Okay? So then we've got certain rules that apply. So in order to be a function in the first place, hang on. Not one, but specifically each output is going input. Man. That's not how you spell input. I'm fine, I promise. There we go. So each input is going to correspond with, at most, one output. So for instance, in the case of a square root function, we're not going to get any negative numbers that go into the function. So all of those potential inputs are then eliminated from the domain. And they're also just considered not valid. So negative numbers into a square root, we're considering them not valid. If we're doing a real valued function, which, again, kind of depends. So that's the rule for being a function. So then, in order to be one-to-one, each input is going to correspond with exactly one output. Now, what does this mean? Right? More generally, if you remember the whole functional inverse sort of thing, that means that we have to go both ways with this. So if we've got, you know, like negative 1, 0, 1, 2, or whatever, and then 5, 3, 8, 1, whatever you got over there, this means that in order to be a function, we can only go this is a bad example, or bad picture, really. So when you've got a whole bunch of inputs, they correspond to a bunch of outputs. But each one only corresponds to one output, and they're also different from each other. So when they correspond, it's kind of going both ways. You're saying that not only is this a function, but the reverse is true. That all of our y values, all of our outputs, only have one thing that they come from. So again, we can trace it back. You can trace it backward and get the exact same behavior going this way too. Hey Bertram. Good evening. 26 stacks. Sound good? So that's functions and one-to-one. The last one you asked about is onto. Correct. Yep. y equals x squared is not 1-to-1 unless but y equals x squared, comma, x belongs to 0 to infinity is 1-to-1. So there may be like a certain restricted domain over which a particular function which wasn't 1-to-1 over an unrestricted domain is 1-to-1. So that's saying that A is going to be your input set, B is going to be your output set. All right, and onto means that every single element in the output set is going to be covered or corresponded to from one of your input sets. Doesn't have to be the same. Doesn't have to be. Could be. Doesn't have to be. Now, I believe, let's see if onto-ness has the Right. So something can be 1-to-1 and be onto. Something can be 1-to-1 and not onto. Something can not be 1-to-1 and be onto. And something can not be 1-to-1 and not be onto. So there are 4 different behaviors that you can get, and all 4 of them exist. Now, did they say output set or... Are you just getting in here, Bertram, or is that a actual agreement? So bijection is 1-to-1 onto. So it has to be both. So 1-to-1 is injective. Says that right, no elements of B are mapped to by 2 or more elements of A is injective. Onto is surjective, which says that nothing in B is going to be left out. And so bijection or 1-to-1 onto has to be both. So those have a what it's called 1-to-1 correspondence. So everything is covered, nothing is missed, and yeah, true. Nothing is missed and nothing is repeated is going to be 1-to-1 and onto. So maybe that'll help. So bijection. One-to-one and onto. Everything is used, nothing is repeated. Onto was our surjection. Right? Everything in the target set, everything in the output set is being used. But it doesn't say anything about like repetition. So you could have a surjection that has repetition. So y equals x squared, for example. Just unrestricted y equals x squared is perfectly fine for an onto. For positive real numbers or non-negative real numbers. Yeah. Yep. One-to-one just means that you can't have any repetition at all. Injection. Injective, surjective. Okay, how's that working? Yeah, I mean, to be fair, so do I, 26 decks. I don't actually teach discrete. That's one of the ones that they've been, like, slowly nudging me toward teaching, and I'm just like... Like, they also want me to teach linear algebra, and I'm like, yeah, that's going to be interesting. So for area of the curve, area under the curve, so anytime that you're doing calculus, you're going to be subtracting right, this is going to be like capital F of B minus capital F of A. Which is going to be A to B like this. Note what direction it is, not just left, right, but this is the positive side, this is the negative side. So if you're trying to, for instance, take an integral from C to D of g of y dy, then you're looking this way. So what do you want to do with this? Again, same deal. This is C, this is D. This is going to be g of D minus g of C. So we're always starting with the highest values in the most positive direction, and then subtracting the evaluation at the lower. If you're not doing that, remember that this can trade your limits of integration at the cost of a negative out front. Okay, so we're doing the remainder. We want right, this is the remainder at any particular n value, which is going to be like as far as we, I don't know, r sub n. To a certain number of positions at x, which is going to be equal to f, or I guess in your case, g n plus 1th derivative at your particular c value over n plus 1 parentheses factorial multiplied by x minus a raised to the n minus 1. Where c is going to be between x and a. Or between x and a that way, whichever way it is. Okay, so then Taylor polynomial, they say then we can replace this top thing with m, and this has to be absolute value. It's an x plus 1, I think. It's always been x plus 1. I don't know where I got the minus from. Okay. So a remainder is going to be less than that amount, absolute value, where absolute value f or g. And n plus 1th derivative at x is going to be less than or equal to m. So m is going to be considered our upper bound for this particular function on this particular interval, where again our function is going to be the n plus 1th derivative. N plus first, n plus 1st, n plus 1th derivative. Yeah, I'd say power series can become one of the most powerful things that you can do, not to belabor that point, but so the way that you had this, we were trying to find for Taylor 1, okay, so g of x minus t sub 1 of x is going to be less than or equal to, so that we got this stuff over here. So this is going to be our again, technically it's going to be the absolute value of g. This is Taylor 1, so yeah, we need the second derivative at some particular c value, which is going to get us our maximum, over n plus 1 is going to be 2 factorial, which is just 2, multiplied by the absolute value of x minus a. So you said that a was going to be -1, hence making this x plus 1 raised to the n plus 1 power plus 1, jeez man, n plus 1 power being 2. Okay, so g double prime at c has a maximum value on the interval. We can find out what it is, and you have that value is 20. So this is going to make then 10 times that whole thing. G double prime at c ends up being 20, or at least the absolute value of this thing equals 20. So then r sub n of x is going to be equal to, this is 20 over 2, factorial is 2, absolute value x plus 1, and then squared. So you had 10, absolute value x plus 1, squared. Less than or equal to. N is 1. So r sub 1 of x going to be those. So this is again R1 on this side. Okay, so then going with absolute value g of x minus Taylor 2 of x. This is then going to be less than or equal to absolute value g triple prime at c, or c2 or something, whatever it is, over 3 factorial is 6 multiplied by x plus 1 cubed. Alright, so without knowing what the actual function is, we won't be able to test like what this is going to be. You can let me know what it is if you want, or we could just kind of do thought experiment about it. I don't really care which way. But in your formulation, you said that g triple prime at c is going to have a maximum value of 10. So 10 over 3, x plus 1 cubed, like that. Do the applications involve? Alright, so test that when x equals negative 0.9, then match the answers in the previous part. So yeah, if you plug in negative 0.9 for each of these things, we end up with a positive 0.1 inside the absolute value, and then you can square or cube and multiply that out. Wait, that's supposed to be a 6. Oh, 20. I get you. Okay. Huh. So the maximum value of g triple prime at c, you know, some new c value, is probably not going to be, also going to be 20. It could be. Okay. Due to the applications involved, we need an error in absolute value of at most 0.01. And so for what values of x respectively can we use t1 or t2 in place of g of x? So where do we want to be able to use this? How far are we allowed to, given that our actual absolute error limit is 0.01? So really what we want here is that 0.01 is our limit. So for what values of x is this going to work? So we can divide by 10. R sub 1 of x has to be less than or equal to 0.01. Which means that, again, it's going to be the absolute value of x plus 1 parentheses squared has to be equal to 0.001, 1/1000th. we take the square root of both sides. This is going to be the absolute value of x plus 1. Is equal to 1/1000th, so 1000 to the negative 1/2 power. So the interval over which this works is that x has to be from -1 minus 1/1000th to the negative 1/2 power up to -1 plus 1000 raised to the negative 1/2 power. I mean, I don't, because I don't bother, because if somebody doesn't know their stuff well enough by now, it's not going to help them. However, typing everything into your calculator will, well, it'll do better if you manually scribe it using, like, pen and paper. Well, sort of. So there's a connection that, for whatever reason, human beings began evolving our written language a bit more over the past several thousand years, to the point where, like, the people who survive the most are the ones who, generally speaking, have, you know, the right brain connections to be able to read, at least in some way, shape, or form. And as it turned out, like, doing all this digital stuff is not at all like working with our brains almost at all. It's basically like moving arbitrary images around. Just doesn't do anything. What makes a much greater connection is like physically writing something. The muscle memory of actually writing something out ends up doing way better things for your memory than trying to type things. So even the act of writing something out ends up helping you learn it better. What do you mean, kinda true? There's research been done on this. I mean, everyone wants digital stuff to be, well, yes. Everyone wants digital stuff to be easier and to just be like, oh, well, I can just manually do it. It doesn't make the brain connection anywhere near as much as having the muscle memory. And it's just, again, because we haven't been conditioned to this stuff yet. And like we, those people who are actually here, sure, we probably have a slightly better connection with electronics than your average person. But nonetheless, it still just does not stick as well for whatever reason. At some point in the future, I think I want to get a caracorder and play around with that thing. Because that is gonna... That's so messed up, but it's so awesome. No, caracorder. So it's basically like little plungers that are kind of like analog sticks on controllers, but they have 10 of them. They're arranged in the shape of where your hands go, and then you like move each of them in a certain direction to choose letters, but you do them all at once. It's not like, I mean, you can do them manually one at a time and come out with, your standard 100, 200 words per minute, something like that when you're typing. Standard 1 to 200 words per minute. But they've actually found out that what you can do is that this thing allows you to chord, like when you're pressing keys on a piano, right? You can do individual notes one at a time, and it gets you to do this nice sort of music. But if you chord your input to a piano, you get multiple notes at the exact same time. So if you chord your input for a particular set of letters, the computer inside the caracorder will automatically process and then use, machine learning to try to figure out what word it is that you're actually trying to type. So you chord all of the inputs at once, and then it just instantly comes up with like a couple of options as far as what it thinks you should be typing. So it's an ingenious design. It's unfortunately like $300, so I'm like, I can't justify that. But maybe someday, when I've made my millions or whatever. Yeah. So it's a little bit like stenographer, being a stenographer, doing shorthand, like all that stuff. It's a little bit like that. And they've what I really wanted to do was not just use it for just typing, not just typing, but also for inputs for flying, and try to do Elite Dangerous. Like you could do literally all of the inputs at once for whatever you need. So you could be doing pitch, roll, and yaw all at the same time flawlessly, and then using thrusters as well in whichever one of the 6 directions or multiple of the 6 directions that you want at any given time. So, like I said, you've got your pitch, you've got your roll, and you've got your yaw, but then you've also got up, down, left, right, and forward, backward thrusters. So, like, that's a potential for what? How many different things can you do at once? So that's 3 dimensions plus three thruster dimensions as well. So you could input 6 things at once. I'm pretty sure that this keyboard yells at me if I do something like that. And like lately I've been trying to do I've been trying to fly using both keyboard and stick, and it also doesn't really like me doing that, but it works sort of. I think my biggest problem is that whenever I'm using the stick, like I need to hold the base with my other hand, because otherwise if I twist or if I pull in one particular direction, it's just gonna like, it doesn't have anything to push against, right? Like it's not on a desktop where it's going to push down against the desk. It's on my lap, which doesn't really work. I could figure it out someday, but today is not that day. Alright, so hell with it. Let's do something. Sublanelin. G of x here is going to be, let's do natural log of x squared. So t of x is going to be equal to, and I don't remember what my actual Taylor expansion is of natural log. It's in here somewhere. I'm sure there's a... There we go. There we go. So t of x is equal to right. A here is going to be equal to 1. So we don't want to get too close. So this is going to be right. Normally it says x minus 1 minus a half x minus 1 squared plus 1/3 x minus 1 cubed minus, and then dot dot dot. This just keeps going on. Now in this particular case, we've got x squared, which is our variable term. So all of our x's become now x squareds. Okay, so if this is the case, then our Taylor 1 of x is going to be equal to this thing here. Just x squared minus 1. Alright, if we are centered, okay, g prime at x is going to be equal to 1 over x squared times 2x, which is equal to 2 over x. G double prime at x is going to be equal to the derivative of this thing is going to be negative 2 over x squared. And just for good measure on the next one, going to take a negative 2 down. It's going to make this 4 over x cubed. Sure. Go for it. I will be finishing this just real quick in the meantime. Okay. So on the interval, we want to have like let's say that x was, well, let's just do, right, r sub 1 of x is going to be less than or equal to going out to 1 g double prime is going to get us this thing. It's going to be the absolute value of negative 2 divided by, let's say we're only going to go out to like 3/4. So this is be like 9/16. Because if we go any further than 1, wait, yeah, because this is going to be bigger than negative 2. Okay. Over 2 factorial is just 2 times x plus 1 squared. So then here we divide by 2 in both top and bottom. That's going to go away. So it's just going to be 16 over 9 multiplied by the absolute value of x plus 1 parentheses squared. So I was saying here, arbitrarily chosen x equals 3/4, just cause. So if we're staying somewhere within like 1/4 of, oh, minus 1. Oops. Okay, so if max distance is 1/4, then we end up with r sub 1 of x is going to be less than or equal to 16/9 times 1/4 squared is going to be 16, so that's going to be less than or equal to what? This is equal to, but r1 of x would be less than or equal to 1/9. That is 0.111 repeated. Not great, but, you know, something. Alright, and likewise, r2 of x is going to be less than or equal to, that's our third derivative, so it's the absolute value of 4 over x cubed. X cubed, which again, we can arbitrarily choose, in this particular case, 3/4 to go in there. Oh, let's see. X minus 1 raised to the third power. And that's not a 2, that's a 6. 3 factorial. 3/4. And that allows us to define the max distance. So R2 of x is going to be less than or equal to, this is going to be 6. 4 over 6 is going to be 2/3. And in this particular case, we get a denominator of 3/4 to the third, so that's going to flip under, make 4/3 to the third, times x minus 1 cubed. Okay, here we get 128 over 81. Times, again, if this is max distance of 1/4, that's going to be 1/4 cubed, which is less than or equal to 64. 128 over 64 is going to be a 2 up top, so 2/81. R2 of x. Okay, so similar to the other one, it's just kind of arbitrarily chosen, which maybe it's not the best idea, but whatever. We're just kind of spitballing stuff at this point. Look at how the relationship changes. All right, let V be the volume. Yeah, well, let B be the volume of a solid obtained by rotating about the y-axis. So that way. Rotating about the y-axis, a region bounded by square root of 4x. Y equals the square root of 4x is crunched this way. Okay, and y equals x squared over 4, so that's also going to be crunched, or that's going to be allowing it to go out further. Y equals 1/4 x squared, and y equals square root of 4x. Find the volume of this thing as it's going around the whole. That doesn't, no. Almost. That's better. What's up? So one is going to be discs, right? Or in this case, washers. Just going to have you go this way. All right, you've got your dy, and you've got your function, which is going to be it's just going to be the other way. So these are going to be inverse functions of these things. They have to be functions of y in order to find out what the top and bottom are going to be. So this is going to be instead y squared, and a fourth y squared equals x. And then this one is going to be, interestingly enough, right? Square root of 4y is equal to x. They're just opposites, or they're inverses of each other. So that makes it really nice. All right, there we go. So this is going to be, yeah, because you're doing everything in terms of a function of y, because you've got to take your differential as dy. So here, this is going to be x1, and this is going to be x2. So here, this distance is going to be represented by x1 minus x2 in order to keep a positive value. So x1 here is larger positive number. Subtract a smaller positive number. So doing a washer ends up with the pi times the integral of r1 minus r2. Nope. Nope, nope, nope. r1 squared minus r2 squared. Right, times dy. So again, doing the whole washer, we're thinking, how do you get the volume of this cylinder that we're creating here? Here, and then here we're chopping a bit out of it. Right, not to scale. So this cylinder here is going to be found by doing right, pi r squared for the big one. Pi r squared for the big one minus pi r squared for the small one times dy gives you the height. So pi r squared for the large, it's x1, pi r minus pi r squared for the small one, r2, x2. Times dy. So pi integral y1 or x1 is the square root of 4y minus x2 parentheses squared minus 1/4 y squared parentheses squared dy. And integral is going to go from y value of 0 up to where they equal, right? 4. It's 16. 16 square rooted is 4. 4 squared is 16 divided by 4. Yeah. Cool. No, don't do that. No, actually do that. So here this is 4y, and then minus here we've got a 1/16 y to the 4th dy. So then we got pi times, here 4y becomes 2y squared, minus, we're raising this to the 5th, this is going to be 1/80th y to the 5th. As we go from y equals 0 to 5. 4. Man. That's just no. Alright, the 0 is going to drop out so that we don't even have to consider it. And then that's going to get us pi times the quantity. 2 times 4 squared is going to be 16 minus 1/80th. 4 to the 5th power is a lot. I don't like that, I don't think. 64, 256, 1024. Yeah, 2 to the 10th. Yeah. E. How much is 1/80th of 1024? Yeah, cute. 64 over 5 is 12.8. Oh, okay. Good. It's a small number, relatively. So this is pi times 32 minus 12.8. So here, this is going to be 19.2 times pi. And that's units cubed. This is where I just don't care. Like, it's perfectly fine. That's nice. And the other thing is that we weren't actually trying to find like what the number was. We were just comparing the two ways of doing this. So option 2 is that we want to do this in terms of shell. So here, we don't want to do this in terms of washer anymore. We said, given this, we want to take this in terms of shell and now create a cylinder type thing going this way. I mean, could have, but so here, this unwraps to make a rectangular prism. The thickness of which is going to be dx. 19.2 pi. That could be a fun one. Did you go from 0 to 0? Yeah. Not really. Okay, so our width of the, or depth of this particular unwrapped rectangular prism is going to be dx. The height of this thing is going to be y2 minus y1. So this is our y2 is equal to the square root of 4x, and y1 is going to be equal to the 1/4 of x squared. So this is then going to be y2 again was root 4x minus, oh interesting, I see it already, 1/4 x squared. It's not quite the same, but it's really close. Alright, one sec. right? So a radius and a height would be very important, yes. So then here, same thing is going to happen going this way. When we unwrap this whole thing, this is going to be this distance going around this object. So 2 pi times our radius, and again the radius here is our x value. So 2 pi times the radius x is going to end up getting us the length, right? The unwrapped length of this rectangular prism. So this is saying that we want to do this over all of the individual unwrapped shells that we're going to do, which are infinitesimally small. And so naturally this is going to be an integral going for x values from 0, right? From 0 all the way out to 4, I'm guessing again, right? 4, 4. It's going to be 16, square root is 4. And again, 4 here is 16, over 4 is 4. Yeah. So 0, 0 to 4, 4. So 0 to 4. This should look familiar, at least part of it. This is going to be our length with height. So root 4x minus 1/4 x squared times 2 pi x times dx. So x root 4x minus 1/4 x cubed, and that's 2 pi out front. So it depends on what you're talking about, right? The radius in the shell case is the distance from our axis, you know, whichever axis you're using. So if it's about the y-axis, then it's going to be an x distance, because you're saying how far away are we from this particular location. So anytime that you're doing, yeah, at least as far as I know, right? Because that's going to be the that's going to be the like only real place where it uses both functions is going to be in this space. Now, it could define other spaces over which it wants to rotate the thing, but if it's defined by these two functions, then yeah, this is the only reasonable place that we would use. So not really. So what you've got here is that we're drawing in a rectangle which is parallel to your axis of rotation. So if your axis of rotation and your rectangle that you're drawing are parallel to each other, so you're going to rotate this way with this rectangle, then you've got a dx as your width of your rectangle. Then the height of the rectangle is going to be your difference in y's. And that means that since you're using dx as your limit of it, not limit, since you're using your dx as the differential, then everything has to eventually be in terms of x. The thing that we were doing over here, this other one here, in the other one when we did the disk method, the reason that we did the disk method was that your axis of rotation and your rectangle are perpendicular to each other. So if they're perpendicular to each other, then you say, well, your rectangle is being drawn with a dy differential. And so that's why everything needs to be in terms of y eventually on the disk method in this particular case. So it always ends up that anytime your axis of rotation is perpendicular to your rectangle, that's disk method. It doesn't matter what direction it's going in. It's going to be disk. If your axis of rotation and your rectangle are parallel to each other, then it's always going to be shell. Okay, so 0 to 4, x root, oh, wait a minute, idiot, of course I can do that, that's fine. Square root of 4 is just 2, square root of x times x is going to be x to the 3 halves, minus 1/4 x to the third dx. Yes, perpendicular is disk, parallel is shell. Okay. Here. This looks a bit better. And there. Nope. There. Yeah, sorry, disk and washer. It's the same thing. So washer specifically is just you have a hole in the middle, so you got to chop out the negative R2 squared. And then you're multiplying it by pi, so negative pi r squared. But, you know, if it's just a disk, then all it means is your R2 is 0. Okay, so here we've got this. This says now that we're going to take the integral of all this stuff. So here, integral of 2 times x to the 3 halves, it's going to bump up to 5 halves. And that's going to get us a 2/5 to balance. And then that's going to have a 2 stuck out front. Well, I mean, the 2 from before. Just constant drags down. Minus. Here, this is going to bump up to 4, and this is going to turn it to 1/16 x to the 4th. Taken where x goes from 0 to 4. So this can be 8 pi over 5 times 4 to the 5 halves. Minus 1/16 times 4 to the 4th. That's 16 squared, so it's going to be subtracted 16. It's not too bad. Okay. And then here, this is going to be square root is 2 to the 5th is 32. So 32 times 8 is going to be 1024. No, 2048. 32 by 8. What was that? 16. Oh, wow. Yeah. No. 25, 256. So 256 pi over 5. This is going to be 51 and change. Oh, yeah, times 2 pi. So this is going to be 16 times 2 pi. It's going to be 32 pi. All right, this is 5 into 256 goes 5 and 1 and 1/5. So this is going to be 51 pi plus pi over 5 minus 32 pi. So 51 minus 32 is going to be 2019 pi plus pi over 5. Got it. 19.2 pi. So we're corroborating this is going to get us the same thing. That's it. Well, times pi. Ugh. Are you using a 4-function calculator? Or scientific? Or, oh, did you use the integral function? Like the one that uses the... So, the thing with that is, this is within the tolerance of the correct answer. So whatever you got for your answer, you divide by pi, and you probably got 19.1999993. That's fine, because it's close enough to 19.2 times pi that nobody's going to make any argument. It's the same when you do Newton's method, or rather when the calculator does Newton's method and you're trying to find the zeros of a particular number on the graph. Basically, it gets close enough to a particular value. Well, yes, but you have to use some thinking about it to be like, okay, well, that is not going to work. You know, 19.1999, etc. is not going to work because it's not that value. No, I don't think you input it wrong. I think that it's, again, it's rounding off to like the 10th decimal place or something like that. And then when you divide by pi, the exact value for pi that your calculator has, it's off by just a slight amount, 0.00000007. But honestly, who cares? Trust me on this. The 19.2 pi is the correct answer. We did it out, you know, it's up there, right? We did all that work to show that this is the actual value. What you do is you say, okay, well, this is what I got in the calculator. Is it reasonably close? Because the calculator is going to just round stuff off wherever it feels like it. It doesn't care what you think. The calculator is just going to do whatever it wants. Now, somewhere deep within the bowels of the memory menu, you can actually manually set the tolerance to be certain values. The more accurate you make the calculator be, the more values it will store in its memory, and then it's only going to spit out the first, 10 to 12 or something like that. Even if you let it go and calculate out to like 16 decimal places or 20, if that's even possible. Um, I think it was. Yeah. This is one of the things that I found out very quickly when I was trying to find zeros on, for any particular function, was that like, okay, well the calculator is going to come up with this value. I got something that's really, really close. The actual value is -3, but I got -3.00000000001, and then the y value ends up being 0.000000003 or something like that. And you know what? The y value being not 0, I'm just looking at it and it's saying, well, the y value is really close to 0, so the x value can be off by at least that much. But probably only by somewhere on that order of magnitude, plus or minus a couple. So, if you're accurate to like the 7th decimal place, um, you figure that it can be off by somewhere around that 7th decimal place. So even out to the 5th or something like that. You'll figure it out. It becomes pretty obvious when you do it on paper and by the calculator and compare your results, because it's like, well, okay, it's pretty close, but I know I'm right. All right. You got anything else? Alrighty. Well, have a good night, Bertram. Anybody else who's here? We're probably going to go over and raid Selena because she is playing Outer Wilds for the first time, and it is my favorite game. So Ugh. Well, good luck at school. Good luck at work. Hope everything works out for you nicely, and possibly see you on Friday or see you next week. Next week is finals for me. I have until Wednesday to slam through everything. Oh, I'm probably going to skip Friday the whatever the hell it is, 16th. I'm probably going to skip stream on the 16th because I got to get my grades in. But I'll still do stream on the 13th because I'm not. Um, that's my finals week special or something like that. We'll figure something out. Alrighty. All right, you too. See you later. All right, we are going to raid over to Selena, who is again playing Outer Wilds. That is not what I want. Nope, I don't want a dashboard. There we go. Great name. Thank you very much for the follow, Quirkle Dirk. Love it. All right, Selena playing Outer Wilds. All right, here we go. And I hope everybody has a great rest of your week. Like I said, I will be doing some streaming for finals next week. We'll figure out what day or days we want to do it. But once Wednesday rolls around, I am going to be committed to completing my exams. So Unfortunately, I will be skipping the Friday the 16th. I'm just going to plan it now. I'm going to be skipping Friday the 16th. So I will see you this week, though. The 9th, we'll try to finish Astroneer, maybe, on the main story quest, and then figure out some of this snail stuff that's going on. So have a good week. See you all later. This is Obi-Wan Pez for N Simplex Pachinko. Have a good night.